All right, chapter 16. This is called normal distribution. And the way I kind of think of it is 13 was theory, pretty much discrete. And in discrete, you had chapter 14 was an example of a discrete, which was binomial. Then you go to chapter 15. That was theory when it's not discrete, so it's continuous. Then you go down to 16 now, and that is an example of continuous, which is normal distribution. And what do I mean by example? It just means that in each context, there is a specific scenario. So you can see that in binomial, that the probabilities are all the same. There's only two outcomes. When that happens, with replacement, you get this scenario to calculate the discrete. For continuous, means you're doing the integral to find the area under the curve, which is the probability. Then normal distribution follows the same idea, but this particular graph, which is what we're going to look at today, that particular graph follows the same properties. That means that it's a probability density function, but there's something more special about it, which is what we're going to learn today. So it's a probability density function. It looks like this symmetrical bell curve, and the area underneath it, there's a lot of properties that we can work with. Okay? So the stuff that I talked about last lesson with transformations, that's probably what we're going to be looking at. If you get it, good. If you don't, you're just going to memorize one of the key transformations or relationships. Okay? Here we go. So, normal distribution. This is the function. Looks scary, looks nasty. Do you need to memorize it? No, they'll likely give it to you if they wanted you to use it. When you type on your calculator, let me get my CAS up. When you type on your calculator and you use, like binom CDF, binom PDF, well, there is a function called norm CDF. And it just means that you're finding the area under the curve, this function. And it actually just solves the integration of this function for you between two intervals. So instead of doing it by hand, instead of typing integration from A to B of this function, norm CDF essentially does that. That's what your calculator is doing. So likely you won't need to know that rule, but if the examiners wanted to, they can give you that and get you to play around and find the expected value, etc. Okay? So what am I trying to say? Let's go to Desmos and I'll show you on a CAS calculator. So let's do it. Calculator, I'm going to go menu 1, 1. Let's define f of x is equal to 1 on square root 2 pi times e to the power of 1/2, was it negative? Yes, it was. Negative x squared. Yes, you can. I think it works with you guys too if you write pi. Is that what you mean? If you just write pi, I think it's pi because it. See how it changes the italics to. Yeah. Well, on a computer, it is life changing actually. Instead of looking for this button over here. All right. So if I were to find the integration, if you were to find the area, you would normally say shift, and let's say from 1 to 2 of f of x dx. Right? Ooh. You get this 0.135, right? If I do norm CDF, so menu, probability, distribution. So you have if you scroll all the way down, so we've got binom, PDF, binom CDF. We also have inverse, which I've taught. And then if you go down, did I miss it already? Oh, it was up here already. Whoops. Norm CDF is up here. So if you type norm CDF, now the lower bound, which I said 1, and I said all the way to 2, so that's my boundaries. The 0 and 1, I'll explain what that is soon, but the 0 and 1 is your function. So your current function is 0 and 1. The mean is 0 and the standard deviation is 1. Okay, so that's for the function that you're seeing on your sheet there. If I press OK, you get exactly the same thing. So what I'm trying to say is when you type norm CDF, it is calculating the interval 1, 2 of the function, which is the one we just typed. Okay, so you got either by hand, or every time you do norm CDF, that's what it's saying. Okay, so the question is, what is that 0 and 1? Well, the curve, if I go to Desmos just to show you, whoops, I just added on something by accident. What did I do? Oh, yeah. Where's my Desmos? Desmos. Oh, yeah, I was playing chess. That's right. Studying chess. Yes, I know. Oh, look at me going to automatic chess. Chessmos. What? Oh, that's pretty cool. All right, so let's type it in. F of x is equal to 1 on square root of 2 pi e to the power of negative, whoops, how do I do that? 1/2 x squared. There we go. So I'm going to zoom in. So this is your symmetrical shape, right? It follows a probability density function in the sense that if you found the area from negative infinity to infinity, because there's an asymptote there, negative infinity to infinity, the area will sum to 1. Okay, so that's already one of it. Area under the curve is sums to 1. Number 2 is that f of x has to be greater than x-axis, or greater than 0. So therefore, yes, it's a probability density function. Now, the nice thing about this particular curve is the mean is actually right at the center. Number 2, what's special about this curve is it's symmetrical. That means that the area from negative infinity up until 0 is actually 50%. And then from 0 to infinity is another 50%. Okay? So it's not only symmetrical, it follows a probability density function, but it has a mean, and this second thing is really cool. Mean is 0 and standard deviation is 1. Now this is cool because I'll go back to the, not chess, but I go back to this. So each value on the x-axis, which we call the z-axis, okay, this is called the z-axis because it's the symbol we use for a standard normal. When they say standard normal, it means this function, because this is the original function. This is when the mean is 0 and the standard deviation is 1. So they use z to represent that. And what's nice about it is, because we can calculate that this is the 50% mark, in the next part of the exercise, you'll find that one standard deviation, when you go one standard deviation from the mean to the left, and one standard deviation to the right, it actually accommodates approximately, and notice the word I said, approx, because it's not exactly 68, approximately 68% of the data. So in the next exercise, 16b has these symmetry properties where it follows the 68, 95, and the 99.7%. And what it represents is every time you go one standard deviation both left and right, it's 68% of the data. If you go 2 standard deviations left and right, that's 95% of the data. And by the time you go to 3 standard deviations from either end, that is 99.7% of the data. Which, if you think in terms of your study score, it follows exactly the same idea. It follows this idea where instead of the mean being 0, what's the mean for a study score? 30. Anyone happen to know what the standard deviation is? 7. So it means that from 30, if I drew a symmetrical one, whoops, that's pretty bad. We're saying that it's 30. One standard deviation is 7 units away. So you get 23 to 37. 68% of you on average will get between 23 and 37. So in this class, if I had to predict, about 68% of you on average on most classes, just in general, will get between 23 to 37. So if you wanted to calculate, when students tell me I want to get a 40 and above, you can actually use this chapter and understanding to actually calculate. If you want a 40 and above, exactly roughly how much or what percentage of the state should you be at? I mean, you can kind of roughly guess it. If I said 2 standard deviations is 95, Well, another 7 will give you 42, and another 7 down this direction will give you, what's that? 16? So for 37 plus 7? Also 34. 44. Couldn't add my 7s. 23 take away 7 is... What's that? 16? From here, this is 95% of you will sit between 16 to 44. So you can, and we can actually calculate the percentage, especially with the change in the mean, and I'll teach you how to do that. But you can actually calculate percentage, how much roughly would it be from 40 and above? To get a 40 and above, and that's where they say top 7%, top 8%. That's where it's coming from. Okay? I'll show you that soon, but here's the idea. So let's not tangent away from the idea. If you get 50 or above, defaults back to 50.
It's between 0 and 50, right?
Yep.
Median's 30.
Yep.
Not 25.
Not 25. Yes. So remember there was a reasoning. Continuing. So what do you take out of this? I wanted you to understand this represents norm CDF, but specifically A to B, 0 and 1 being your mean and standard deviation. So make sure to have those notes in so you understand. I already wrote it here. Mean 0, standard deviation 1. This is called your standard normal distribution. Can you please highlight that or underline this word? Because in your exams, they will subtly write that, and unless you know what you're doing, it's pretty obvious because they say standard normal, but there is a difference in the questioning. If they say that this distribution is a standard normal, they're implying to you that the mean is 0, standard deviation is 1. If they don't say standard normal, they say normal distribution, then that means the mean does not necessarily have to be 0, and the standard deviation does not necessarily have to be 1. So the example we just did before, your study scores, that would be an example of a normal distribution, but not a standard normal. Okay? Everything comes back to the standard normal. So all that percentages I just said, all is on a standard normal analysis. Okay? So we like this. We like the standard normal. But the reality is that in life, not everything has a mean of 0, and not everything has a standard deviation of 1. In fact, there's probably nothing. Okay? So because of that, what do we do when our distribution is not a standard normal? Because we like that curve. We said that curve was symmetrical. We said that curve has a mean of 0, and it's nice that the standard deviation is 1. But in reality, that's not true. That doesn't happen. So what they've done here is they've used the idea of transformations from 15D, and they said, well, what if I applied that transformation? Because it means you shift the mean. So you remember how I said standard normal starts at 0? Well, in a study score of 30, your mean now is somewhere over here, and your distribution could be different. It could look a bit more skewed, right? But the mean is 30 here, and standard deviation is different. So mean is 30, standard deviation is 7. So what they're saying is, well, actually, isn't that just a dilation effect to this original graph? And isn't that just a translation to the original graph? So there's a translation to move the mean away, and there's also a dilation to affect the shape of the graph, hence standard deviation. So based on what we can see here, this transformation that you learned from previous exercise 15D is applied to this function, and right there, where x is being replaced, is right here. Your function, your standard normal function, is being replaced right there. That is your horizontal transformation along with a counter dilation. Okay, the dilation is to, that counter at the front is the counter dilation, which is why you have this. Okay, so we say it's a dilation of factor of 1 on A from the x-axis, because if you skew it horizontally, you need to balance it so the area is still 1. That one's your translation with the dilation. Yeah? So, what's important is, and now notice this bit that I wrote here. probability of x less than equal to x. This is essentially me saying, if your mean's not 0, so we don't know what the mean is, right? But the x value is something. So the x-axis is still x, right? That's your data. That's the real-life data. The real-life data could be somewhere over here. Let's call it A. The probability is essentially the area under this curve less than or equal to A. So that's what I'm writing here. Yeah? So I'm saying the area for the real-life data, that probability is equivalent to if I was able to transform this graph back to the z value or z distribution or the standard normal distribution. Because the thing that we know is this is your normal distribution. This is the transformation because that essentially describes the change, right? So if I know the mean and know the standard deviation for this, I can apply it back to this and bring it back to the equivalent z value. Meaning, what is this? Transform back to my z value. Because if I know my z value and I know the mean is 0 here, I can actually work out the area from here. The area of this will equal to the area of that. Does that make sense? So I'll draw it again. Whoops, I'll draw it again just so you can see, because that's what this exercise or this chapter is really doing. They're just moving back and forth between reality and the standard normal. So your standard normal looks like this. This is your ideal. Mean, standard deviation of 1. That's what we love because we know these negative 1s and 1s. We know the areas of this curve. But in the reality, this is not true. Reality, your study scores are based on this. So what we do is we say, if you had a score of 40, right? And we wanted to know what's the chances for the below. So what's the chance of getting less than 40? Well, then this 40 can be transformed back to figure out what is the z value that corresponds to an x value of 40. So this is the real. Transforming this back to find a z value, because if I know the z value, I can actually work this out using norm CDF. Because norm CDF, or the function, you're just doing the integration from negative infinity up until that z value. Does that make sense? Yeah? So that's what's nice about it. But the nice thing about your calculator is you can actually change the mean now and change the standard deviation. But back then, they only had a mean of 0, standard deviation of 1. They actually had a book, a z values book, that they would follow. And that's why it always comes back to converting it to a z-axis. Now you don't have to. As long as you know the mean and you know the standard deviation, you can type on your CAS norm CDF and it will do it. But back then you couldn't. So you always have to transform back to the z function. Does that make sense? Boys, can we not speak while I'm speaking? Thank you. Yeah. So, most of it is all by CAS. If they get you to do it by hand, they'll give you the function, and they'll like the next example will do. Then that's when you do it by hand, or by CAS by hand. So here, how do you transform a 40 back to this? Well, that little box that I got you to write here. That z transformation, how do I work out z? Z is actually equal to whatever you transform the x value to. So the x value is x, or I called it a here because I said x equals a. But essentially it's your real data minus your mean divided by your standard deviation. Can you write that down? Because this is one of the key transformations that kids don't understand why. And you can memorize it. If you don't understand the transformation bit, you can just memorize that bit. That is how you convert. That's the relationship between your x data and your standard normal. So in our example, if you wanted to know what the z value is for a score of 40, right? 40 is the value that you want. That's the real data. The mean for getting a study score is 30. So 40 minus 30, and then divided by standard deviation of 7. This will give you the z value. Okay, so if we did that, let's do a z. What's that? 40 take away 30 is 10. 10 on 7. So z is 10 on 7, right? So if you think about the graph, 10 on 7 is roughly what? 1.42. So if you look at this, mean on the z graph, not the x graph, this is the hypothetical one, standard normal. One standard deviation is around there. So 1.4 is just almost halfway to the next standard deviation. So it's roughly here, right? So I'm going to write here. Let's visualize it. This is 1 standard deviation to the left and right, and then 1.4 and 2 is over here. So 1.4 is roughly there. So if you want to know what the chances of getting less than 40 is, well, let's do the calculation again. Standard normal, you can do, because I already defined the function, right? So that's the function. So I can go, all right, well, let's do the integration of your f of x, but I want it from negative infinity. So negative infinity up until 1.42857142857. Yeah? So that's your z value. That function was the standard normal function, right? You've got a 92.3% chance to get less than 40. That's a set. So if you want to work backwards then, to get 40 and above, minus that. That's the opposite of that, right? You got to be the top 7.6% of the state. That's where the stats come from when we say it. But you didn't have to do the integration by hand. You could have done norm CDF as well. So we could have done the same thing, norm CDF, and I could have done from negative infinity, I don't know what the O was for, negative infinity up until 1.42857142857, and I'll get the same thing. See what I mean? So am I making it clear with the instruction about the function and norm CDF? Norm CDF is the function. Yeah. Oh. Oh, because you got the yeah. And that's what I'm trying to say. Back then, we couldn't do that on the calculator. So back then we did do 30 and 7, and we always had to convert it back. So that was one of the skills. That's why this one was important to understand. But for you guys now, what's nice is you can just literally type in norm CDF, negative, everything's all the same, but except this one is to 40, and you know the mean, and you know the standard deviation, you get exactly the same thing. So that's nice because you can actually change this back then we couldn't. In fact, my time, I just got into it, whereas the time before me, my teachers, they had a book. They had a Z book, Z distribution book, and a log book as well. So to do all the logs, they had to learn change of bases. To do all the areas, or for Z distribution, they had to use a Z book distribution, which I don't even know how to use. I don't understand it. But I remember them telling me, like, you just read this, read that for each decimal, and that's what they had to do. So you guys now have a CAS, and that's just to understand what is the CAS doing, rather than just typing norm CDF. Because I could have taught you and just said do norm CDF, but I wanted you to see the relationship with the function. Okay, so the examiners sometimes will give you the function, sometimes they don't, and I can't remember if it's on your formula sheet or not, but you might see that original function right up there. Okay, so that's called your standard normal graph. That's the graph for the standard normal, which means mean is 0, standard deviation 1. So far, so good? All right, let's do the first question then. So that's the theory. That's the theory. So let's flip to example 1. This is 16A, question 3. Let's have a look. So they give you the function. This is getting you to get used to this idea. All right, out of curiosity, if you got this function, what is the mean? What is the standard deviation? So if they gave this to you, what is the mean? What is standard deviation when you look at it? You should be able to tell just from reading it. 2 and 3. Standard deviation is 3, so this one is a hint. That's your standard deviation. That's your mean. Okay? So you can do norm CDF already. You can answer this question doing norm CDF on your CAS as well, but we're doing this way. Okay? So we can already say mean is 2, standard deviation is 3. They're asking you to use your calculator to find the area of f of x, which you should be 1, but let's show it. So here we go. I'm just going to delete all of this. You have two ways to do it. You can define the function, which I'll probably do, or you can do norm CDF, and it would have been the same. You just change the mean and standard deviation. So here we go. I'm going to define the function. I got f of x is equal to, what was it again? 1 over 3 times the square root of 2 pi, was it? Yep, 2 pi. E to the power of x minus 2 over 3, I think it was. Oh, yeah. That's right. I wouldn't have this technology. Dx, is that right? Yes, that's good. Okay. And we're now doing integration of negative infinity to infinity. Whoops. Of f of x dx. Whoops. And it should be approximated to 1. Now, same thing had you done norm CDF. If we did menu, probability, distributions, norm CDF number 2, so menu 552, negative infinity up until infinity, so lower bound, upper bound, and 0 and 1, mean is 2, standard deviation is 3, you get 1, same idea. Okay, so both of them are the same. So we should get, use a calculator to find, so we get 1. Great. I've done the CAS work. Now they say, part 2, part B. Express e of x as an integral. So how do you express e of x? Remember, e of x is the mean. And from chapter 15, you learned that the mean is this formula that I've got up here. Right? So it's x times the probability of the function. So right as an integral, essentially you're doing integral of negative infinity to infinity of x times 1 on 3 root 2 pi e to the power of negative half of x minus 2 on 3 all squared dx. They say calculate e of x. I know. I wonder what that's going to give you. What is it going to give you? Yeah, so let's try it. So I'm going to do this, put an x at the front. I'm verifying, yeah.
How did you know it was equal to 2 without putting it in?
Because,
Well, you can look at the graph.
yeah, or the equation. Because, oh, wow, this is all, I'll be jumping. Remember how I talked about, we essentially had a graph, and we read from the equation before that the mean is 2. So, mean is 2, then you find the expected. The mean has to be 2, just from reading the graph there. But we're verifying it. Why is it shifted?
We got 2.00009. That's because
I actually have no idea.
All right, so we've just proven mean does equal to 2, which we already knew from the beginning. Mean of 2, standard deviation of 3, and this was equal to 1. And so find the standard deviation. What would the standard deviation should be? 3, but if you were to find it, see, let's say you didn't know that because you haven't understood the theory, but you know the formulas for it. How would you do it? Well, we've got variance up here. E of x squared, take away the e of x all squared. E of x we just found out was 2, so e of x is equal to 2. How do you find e of x squared? Yeah. So it was just the same thing. It would be x squared negative infinity to infinity times f of x. So let's try that. Here we go. Ex squared gives you 13. Beautiful. And if that's 13, well, putting it together, variance of x is equal to e of x squared, take away the mean all squared. So you got 13, take away 2 squared. That gives you 13, take away 4. Then take away 4 is 9. But remember, standard deviation is the square root of variance. So you can see standard deviation of x, square root of variance. So root of 9, 3. So we've proven it. We've shown that yes, that is true. So even if I didn't know the theory just from reading the transformations, I could still apply using the function. Okay, so hopefully you see that linking. That was one of the key things from 16a. All right, so 16a is to get your head around standard normal versus normal distribution. So this function that you're seeing, that's normal distribution. That's normal probability. The other one is standard normal. Okay, so when you read the question, make sure, are you checking, is it standard normal or is it normal? That's the difference between the two. Yeah? All right, team. That's 16a. Let's go to 16b now. 16b is just a bit of problem solving. It's a bit more fun. Those who do general, you would have seen this already. 16b, this is called your 68, 95, 99.7. You do need to know them. Okay, so in the general class, they usually get this graph. So it's broken up for you. I mean, you can calculate that yourself. You know, from here to here, it's 50. If you already know that 1 standard deviation below, 1 standard deviation up is approximately 68%, well then, you can divide it by 2. 68 divided by 2 gives you 34. So that's how you can break it apart. So that little graph there could be useful for you if you're not used to working with, finding the different regions and the areas. But this is 1 standard deviation to the left, 1 standard deviation to the right from the mean. This is 2, 2, -3, and 3. If you're wondering how they knew this was approximately 68, again, standard normal. So you can do it on your CAS, do norm CDF between -1 to 1, and you would get approximately 68. It's not exactly 68, it's approximate. Okay? So, what are you doing in this exercise? You are using that property of a curve to then answer these questions. Let's do this example. Heights of 300 people are recorded. So we've got 300 people here. If the mean is 170, so you know the mean is 170, standard deviation is 10. So usually when I work with these problems, I draw the diagram. So I say it's a normal curve. It's not a standard normal. Mean is 170. Standard deviation is 10. So that means 1 standard deviation across is now 160, 180. So this is now 1 standard deviation across. Here's the center. And then if you do another one, so 2 standard deviations across, that's 150. 3 is 140. This is now 190, 200. So I'm just splitting it up into your 1s, 2s, and 3s. So you got your 1, -2, -3, that's your 0. And that's your 1, that's 2, and that's 3. Okay, now let's answer the question. The question asks you, what percentage of people are expected to have the heights between 140 and 200? 140 is over here. 200, I wrote 20 there. Whoops. 200. So you're asking this. All these people who sit between there, what would the percentage be? Now that's really just 3 standard deviation to the left, 3 standard deviation to the right. So what's the percentage? 99.7. Very good. So you just got to remember 68, 95, 99.7. That's what this property is. Yeah? Next one. What about between 140 and 190? So 140 to 190. So 140 is still here, and I'm going all the way to 190. Oh, you're 190.
No,
Oh, wow. I didn't even know that. Man, that's unbelievable, actually. Wow, it's crazy. 195. Oh, and 190. So, how do we work that out? And again, you can look at this graph here. You can use the property. That's just up to 2. So you already know that that's from here 2.35 plus 0.15, which is really that 2.5. And then you can take away that 0.15 and you get the rest. But there's a lot of ways here. You could add them all, add all of this, and get that. Or you can subtract 1 take away 2.5 and take away 0.15. And you get an approximate. Get me? So what is this exercise about? It's getting you used to working with the properties of the shape and then answering the questions. I'm going to pause the video. I'm going to give you 4 minutes to answer both the double I, triple I, and then B. Have a look at B and see if you can answer that one as well. 2, 3, 2, 1. All right, as it is to example 1B. So hopefully A was pretty straightforward. I did it graphically, but you could also do norm CDF on your CAS and you've got the answers. But part B. How do you do part B? Shh. Who has an attempt? What attempt would you do? How do you find, if they give you the area, which is the probability, they give you the intervals, what are you missing? Standard deviation.
I'll do is what I did, just trial and error for each. Because you see on this one, it's got this one, so look at different chunks. Just trial and error, which combinations of those which are adjacent to each other would add to A5. I figured out it was the middle two plus 1 standard deviation on one side.
Oh.
And then from there you know that that's 3 standard deviation range, right?
Oh.
So 183 minus 171, that gives you 12. Therefore, you do 12 divided by that 3 to get the 4 standard deviation.
That's very intuitive, the way you're sort of picturing it. That's
I mean, it doesn't matter what side it's on.
Yeah.
They're absolute better.
That's really nice, actually. I was, wow. Yeah, that's a good idea.
You can also do it with simultaneous equation with Z scores and stuff.
Yeah.
But I think that's just easier.
Oh, well, that's a nice one. Yeah, I did the simultaneous. So I just said, if you understand the function, it's the integral between A and B. So I've got the integral right there. You got your function. And you type in your CAS, solve for standard deviation. But this right here, what I'm typing there is a CAS function because we already know CAS norm CDF gives you the area. Then there has to be a reverse. And there is a reverse on your CAS menu, probability, distributions, inverse norm. Inverse norm is the same thing as what I just said here. You're essentially just doing the reverse. You've got the area, they just need A to B and what your standard deviation or normal is. Okay, so, but one caveat though, this one usually is better if you convert it back to the Z value to then figure out, because that's got a mean of 0 and a standard deviation of 1. But you could call it X and then do solve for that, solve for X as well. Okay. But anyways, let's do what's this answer here? I've got solve. Actually, if I did Z value, yeah, instead of doing simultaneous equations, I think that would have been the other way to do it. Yeah. All right, team. The time. Otherwise, it's me talking for the entire session.